Yeah, so thank you, Alberto. So this is, as in essence, it's continuation of previous talk by Giovanni. So it's our joint ongoing project. So let me perhaps start with the statement that indeed we are claiming, we are proving in the system ATR₀. Right, so, so usual Higman's lemma is a statement that if something is well quasi-ordered, then the order on finite sequences over this order also happen to be well quasi-ordered. Lemma. Okay, so if Q is WQO, then Q less than omega. Quasi-order. Right, and here, of course, you probably remember from the previous talk, we order finite sequences by embeddability ordering, right? So if you have two sequences, something, Q0, Q1, Q2, Q3, and then you embed it in some sequence that is at least S is at least S long, but perhaps longer, and this map should be monotone, right? Maybe there's some gaps, but anyway. And then, so you embed Qi into some Q, 0 prime, and of course, comparison should be less than or equal to, in the sense of the order Q, right? We kind of embed smaller elements into big or equal elements. It's very natural. Okay. And okay, this is was the classical result was that this iteration, when we go from an order to the order of finite sequences, it's a well quasi-order preserving iteration. Okay, and so the result that I will be focused in my talk is the analogous result where we replace well quasi-orders with beta quasi-orders, right? So the question will be if Q is beta quasi-order. And so then we want to show that finite sequences of Q also form a beta quasi-order. So why is this interesting? So basically there is indeed this, as you probably remember from Giovanni's talk, there is a more general result of Nash-Williams. That is that if Q is theorem of Nash-Williams, that if Q is if Q is beta quasi-order, then for every ordinal alpha, Q to less than alpha is beta quasi-order. Okay, and then and in reality we kind of want to analyze in which system of second-order arithmetic this theorem can be proven. However, as actually was already proved by Alberto Marcone, this kind of the hard part of its implication to prove in ATR₀ is the case of finite sequences. That is, what we know by what was the theorem of Alberto is the following. I think 94. Okay. Yes. Yeah, okay. Then I think I saw your preprint was from 94, but okay, because it was anyway. I guess. Anyway, I think kind of at least it was from like first half of 90s or something. Anyway, good. So but the theorem is right. So that so ATR₀ plus let's call this statement so Higman for beta quasi-orders proves Nash-Williams. theorem of Nash-Williams. Okay. Yeah, so really, this kind of what happened to be the case that, in fact, there is big difference between kind of arbitrary transfinite sequences and indecomposable transfinite sequences. And actually, again, so this was perhaps what was seen kind of in the kind of talk of Giovanni, right? So that, yeah, so this kind of the different technique. Basically, we need different techniques to deal with indecomposable sequences and with arbitrary sequences. And in fact, okay, so and every sequence is in fact every transfinite sequence is in fact finite sum of indecomposable sequence. And basically, this is why this kind of reduction does work. Yeah, and okay, actually, I think this technique, this of course, result that could be proved by techniques outlined in this talk of Giovanni. Okay. So yeah, really, so the result that I will be focusing on is this one. Okay, and kind of the broad idea behind what we want to do is we kind of want to better understand these results about beta quasi-orders. So because say the classical method of proving that things are beta quasi-orders is based on minimal bet array arguments. And this kind of quite abstract arguments in the sense like they kind of say, indeed, like they don't allow us to precisely match the reverse mathematical strengths of the statements because yeah, we kind of using this fairly abstract technique. And okay, this kind of allows us to prove things, but then we don't, okay, we kind of don't know kind of actual, say, ordinal content of the statements of things being beta quasi-orders because okay, there's kind of actually big difference between, like, say, current state of the art of how people study well-quasi-orders and how people study beta quasi-orders. Because for well-quasi-orders, we kind of can naturally associate ordinals. That is, like, so basically by the classical theorem of de Jong and Paris, if you're given a well-quasi-order, there is this kind of so actually, first of all, this trivial fact that linearization of well-quasi-order always are well-ordered. And then you by theorem of de Jong and Paris, there is this kind of linearization with maximal possible order type. And hence, basically, this kind of maximal order, possible order type is kind of basically characteristic ordinal of a given well-quasi-order. And thus, like, from for me as a proof theorist, like when I see like kind of ordinals are very tightly connected to theories, and this kind of makes this connection between, say, theories and well-quasi-orders very clean and understandable. Right? For example, I don't know if you say take Higman's lemma, right? We basically know that if say if you have a well-quasi-order Q and its maximum linearization order type is alpha. Then this maximum linearization order type of Q to less than omega is actually, I think I don't remember like the precise expression, but basically you could express it in terms of the two omega exponentiations. There's some subtle cases. Yeah. There's kind of depending like this standard. Because I think usually this kind of transformation, what these operators on well-quasi-orders result in terms of ordinals is they kind of more corresponds to fixed point free functions on ordinals. They're like, anyway, there are a few subtleties, but but basically you kind of dealing with this corresponds to the kind of double omega exponentiation. And thus, like from this perspective, it's very kind of, for me as a proof theorist, it's very easy to see that this statement reverse mathematically should be equivalent to ATR₀, right? Because this is basically because the function ordinal of ATR₀ is epsilon 0, which happens to be, of course, fixed point, the least fixed point of omega exponentiation. Okay, but for beta quasi-orders, this is much less clean, right? So at least as things stand. So because we kind of, at least kind of this, when you look at the beta quasi-orders from the perspective of minimal beta array arguments, like you don't actually see these order types immediately. And yeah, and basically what we hence trying to do is to actually, as Giovanni talked about this, we try to associate with statements of things being better quasi-orders, particular families of well-quasi-orders, and then we want actually to have explicit characterization of this well-quasi-orders. As I say, to have much more combinatorial understanding of this corresponding families of well-quasi-orders. Okay, so now kind of going back to this concrete case, like how we approach it here. The idea is the following. Yeah, so basically, as kind of Giovanni already mentioned, so we so given so Q is beta quasi-order if and only if for every alpha V alpha of Q is well quasi-ordered. Right? And here V alpha of Q is just cumulative, I think, V dot alpha of Q. And so this is just cumulative hierarchy of sets with your elements. Okay, for technical reasons, it's convenient to say that like we want only sets, such that the transitive closure has no empty set in them. Anyway, basically, empty set doesn't do any good from technical perspective, hence it's convenient to remove it, but actually like, for the characterization, it doesn't matter. Like, this equivalence would still hold. Yeah, so, okay, so what precisely are, yeah, and so this is basically, of course, gives us such a characteristic. We need associating this family of family of well quasi-orders to a given kind of beta quasi-order. Actually, maybe I kind of comment a bit more what the families are. Really, the idea is the following. So there is one of equivalent definition of thing being well quasi-order, namely that an order is a well quasi-order if and only if the family the family of downwards closed sets over this order form a well-founded relation under inclusion. Basically, only if say D of Q under inclusion is well-founded. Where D is like all downwards closed, all non-empty downwards closed subset of Q. Yeah, right. So, and in reality, when we are talking about this cumulative hierarchy, what we really want to talk about is kind of about, we want to talk about this iterated downwards closed sets. It's actually one, you could equivalently define it like this. So this, so basically, the order on cumulative sets that we consider is essentially kind of building in the downwards closure, right? And yeah, so basically, kind of alternative realization would be the following: we can construct this, say, restricted cumulative hierarchy only on this hereditary downwards closed sets. It's you kind of start with Q, then you consider downwards closed set of Q, then you consider downwards closed sets in the resulting order, and so on, and you kind of do it transfinite. And you can, as you usually build these hierarchies of sets along ordinals. Okay, technically, this is not very good from kind of from perspective of formalizing things in systems of second-order arithmetic. So this is not how it's done formally, but this is the intuition, right? So basically, just kind of iterate the kind of construction downwards closed sets along all the ordinals. Yeah, and basically this order. I think I'll remind you about the definition of the order on sets, right? So this order is. So X is less Y if and only if it's order on this sets with your elements. So basically, for every X prime there exists so x prime in x, there exists y prime in y, such that x prime is less than y prime. So this is if x, y are not your elements. Then, okay, for your elements, it's simply order on Q. So less than equal QY. If Y are from Q, and yeah, and the last case was X. Your singleton X is small equal than than Y if basically X is from Q and Y is not. Right.
Universal, where you can stop or
for alpha. No, it doesn't matter.
Oh.
No, I mean, but this is simply because being a beta quasi-order is equivalent to every countable suborder being beta quasi-order. Anyway, this is like with well-foundedness, right? So this, an order is well-founded if and only if all its countable suborders are well-founded. Yes. So basically, yeah, so this relation, and as you can see basically this kind of the key clause, of course, the first one. And this first clause essentially builds in downwards closure, right? You can kind of essentially consider like this sets as if they kind of sets X, basically look at two sets X and Y, and essentially say that X is small equal than Y if kind of the downwards closure of X is subset of downwards closure of Y. Or in other words, like every element from X is contained is below some element of Y. So yeah. So yeah. So basically, this hierarchy is really just hierarchy of. So basically, it's like you could say this is like coded. You can see the codes for this hereditary downwards closed sets. This kind of other way of looking at this. Okay. So then how we actually deal? Yes. Oh yeah. This is
because you're looking all at finite sets.
No. They're not finite.
Okay.
No. Yeah. So yeah. So, but then, okay, so we actually, to analyze this, it will be convenient to look at somewhat smaller orders. Namely, okay, here we look at downwards closed sets, but actually the other natural thing would look at ideals. Right? So basically, when instead of kind of go each step kind of looking at downwards closed sets, we can look kind of at each step look at what happens with ideals of the order. So basically, right. So what would be the definition, right? So we kind of say we consider this thing. It's yeah, basically it's hereditary. Hereditary upward directed elements of v dot alpha of Q. Directed. Yeah, and okay, so what happens is that you have equivalent characterization. In fact, so it's kind of, instead of looking at arbitrary sets, we can look at hereditary upward directed ones. That is basically it kind of yeah. So basically, what is if a set is upward, both upward directed and downward closed, this is an ideal. Essentially, we kind of talking about hierarchy, this transfinite generated hierarchy of ideals of higher and higher levels. Okay. So I think kind of the first thing I should explain. So, yeah, and okay, maybe before proving that this is equivalent characterization, let me kind of explain what is the broader plan of the proof. So we basically have this equivalent characterization that kind of. And the idea is that really this kind of orders on hereditary downward clause sets, they are simpler than this original orders in terms of hereditarily downward clause sets. And now we want simply to study them for this particular orders, Q less than omega, right? Okay. And what we are proving is the following. So if you consider this orders, okay, technically we need slightly different variant of this. Like I think I comment on the letter what is slightly different variant, but it's basically the same thing. Q less than omega. We kind of we will show that this is we can have an order reflective map. And this is kind of typical reduction of well-quasi-orders to another well-quasi-orders. Okay, we will have this kind of order reflecting map in this order. Q less than omega. Yeah, this is a bit technical, but this is kind of what it ends up being. So we basically show that in some, so basically if you have ideals here, right? Kind of iterated ideals here, and you kind of, but then it's kind of order inside is order on finite sequences. Then you kind of can push this kind of operation basically this Higman operation through this iterated ideal construction if you trade ideals with downward clause set in slightly more complicated order. It's here it's kind of Q, and like we have disjoint union with ordering. Kind of so it's the same. Basically, we are kind of dealing with this essentially combinatorial characterization of the orders. I haven't defined it. Yeah, so star is actually a closely connected version. So it's basically in the case of star, you kind of a bit more things are comparable. So this is like usual one, and like for star. So this is like you kind of add additional instance here. This kind of
set with a
so you say that like so basically when you sometimes your elements could be bigger than sets, right? So basically you say that if X is not in Q but and Y is in Q. This is the difference. So I mean, actually, in some sense, it's.
So this means that all elements of X are below Y.
Yes.
Right.
Yes.
First lemma.
Yes. Precisely. So there's some technical reasons why sometimes this order happens to be more convenient. So this. Anyway, so kind of a bit more things are comparable there, but then you also can prove equivalent characterization, like you could put stars here and here, it's also equivalent to things being better quasi-orders, which could be achieved by the same techniques, really. So they are kind of, in some sense, they are more natural, because kind of for star orderings, you have this, right? So that V alpha plus 1 star Q happen to be isomorphic to downwards clause set of V alpha star of Q, which happen not to be the case for other versions. Anyway, there's just some, they basically sometimes, this is kind of what is good about them. So they kind of behave in this algebraic, in some sense, like they behave in a nicer way. But in other sense, not like this is a trade-off, because this basically when you look at this non-star hierarchies, you're kind of talking about hierarchies of end extensions, right? Kind of V alpha plus 1 of Q Q and extend the alpha of Q. While for style version, it's not true anymore. Bit of trade-off, like, and for one argument, anyway, there's some technical details here. For some arguments, actually, it's more convenient to talk about this kind of style version of the ordering, which happen to have this nice property. Sometimes this is convenient thing to have, and other times it's more convenient to have them being Kant extensions. So, I mean, actually, you could, these orders, of course, as you saw from the previous talk, they closely connected to the orders on transfinite sequences. And in terms of transfinite sequences, basically, these orders, they correspond to indecomposable transfinite sequences, where you kind of, basically when you compare them by embeddings. And in style version, you actually kind of, you can also consider it's also equivalent to the order on sequences, but now instead of embeddings, you allow this kind of map that could collapse intervals into single points. But you still should have this less than equal condition kind of for all the points within the interval that you collapse. So yeah, so it's kind of, so basically they are closely connected and kind of both are natural version, but then they have slightly different properties. Anyway, this is kind of some technicalities. Okay, anyway, so basically, so basically the kind of the key result that we are interested in is this one, right? So basically, so we kind of essentially, and this basically gives us a reduction, right? So that if you know that this order is well quasi-order, and basically we know this from the fact that Q is beta quasi-order, then we will know that this one is, and that's how the proof in ATR₀ essentially will go. Okay, so now. And of course, kind of mentioning that basically we kind of know a bit more, we really kind of analyze this kind of underlying combinatorial structure associated with U being so Q less than omega being beta quasi-order. Okay, so now how precisely? So then I need to explain two things here, right? So first of all, why this equivalence holds, right? So why is Q being beta quasi-order is equivalent to ideals over Q, iterated ideals over Q being well quasi-ordered, and secondly, I need to explain how this embedding works. Okay, let me start with explaining of this first claim about equivalent characterization of beta quasi-orderness in terms of iterated ideals. And here, the idea is kind of simple. So, in fact, so we, I think kind of, in some, so basically when we have something is a beta quasi-order if it has no beta rays, right? Use BQ if and only if Q is BQ ideal. So basically, by this I mean this statement. Okay. Okay. So basically, of course, hard part is to show that if something is BQ ideal, then it's BQ. Because in other direction, like clearly, so basically this order is clearly kind of is suborder of this order, and hence if those already have been well quasi-ordered, those clearly else are well quasi-ordered, so it's not an issue. So hence basically what we need to show if there is so basically we will of course prove quantification, right? So if there is a beta ray, then there is a bad sequence of ideals. Right? If there is a beta ray F Q, then there is a bad sequence. That in I dot star, here let's consider diversion. alpha where alpha is the rank of the front on which the array is defined. Okay. And so what is the idea? So basically, the point is that in fact, when we have fronts, we kind of, there is this basic canonical procedure how you could go from a bad array to a kind of bad sequence over v dot star alpha of q. And basically the procedure is kind of basically do bar recursion over the front, and you simply collect all the elements that you see. Yeah. So basically, okay. Let me just. So yeah. So basically, what is the front, right? So you kind of could think about, basically about it as a well-founded tree of sequences of natural numbers, right? So you kind of, okay, you start with empty sequence of natural numbers, and then kind of you go to like longer and longer sequences. Technically, in the case of front, of course, like the support is the same, but anyway, this is kind of something. You can just, the point is it kind of well-founded tree. Something like that. Oh, okay, and so basically, you kind of do kind of well-founded recursion over the well-founded tree, and yeah, and so what I forgot to say is that basically front associate to the leaves in this tree elements of the order q. And then you kind of can simply do kind of when you kind of do recursing over the tree, when you reach each next node, you associate with this node basically the set of images of all its children, right? You kind of basically this is here you have q1 and q2, for example. Then to this node you associate the set q1, q2, basically like this. For example, in this node, right? For example, this was I don't know q4 and this was q5, and to this node, hence you would associate the set of q1, q2, q4, q5. As simple as that, right? And then do it over whole well-founded tree. And then, like, it's fairly easy to see that this if you started with a bad array, okay, then you kind of do it up to all levels, but the last one, right? You don't associate anything to like to the root. And what you left with is the sequence of sets. And then it's possible to show that an array was bad if and only if you get a bad sequence of sets. Okay. And now the trick is, okay, but that given a bad array, we in fact can always sparsen it. So an array such that we will be able to guarantee that resulting sets will be kind of from this I alpha. That's right, it will hereditary, this kind of hereditary upward directed sets. And it's kind of not hard to see why it can be the case, basically because, okay, so when you want this kind of upward directness, you simply need to and you collect, basically each next node, you kind of collect the set of all children, you kind of simply need to sparse in the domain, so that like what you left with is just kind of upward directed set. And it's kind of, for people who are familiar with the proof of Klopp and Ramsey, theorem is basically a variant of proof of Klopp and Ramsey. So we're kind of doing, like, actually we're doing this recursion over Kleene-Brouwer order on this well-founded tree associated with the front. And then we are computing sparsenings of the domain of the front, of the base of the front, such that, like, for the sparsening, we will be able to guarantee that the resulting kind of bad sequence of sets consists of hereditary upward directed sets.
Sorry, in which
So bad sequence is like this, right? So you basically, okay, so you associate, basically you have this children of the root, right? And you associated some set to this one. This would be the first element of the sequence. Then you associated some set to the second children. This will be the second element of the children. Yeah, this is kind of. And this,
like on the
Yes, immediate children, yes, this will be bad.
Sequences of like one. These are sequences of
No.
well, they're the sets that you assign to the sequence.
Yeah, sorry. I mean, of course, the root has infinitely many children.
Natural numbers.
Yes. Yeah, so this would be bad sequence, yeah. And then basically by parsing the array, you can guarantee that they are the corresponding set are upward directed. But actually sparsing that it never breaks badness of arrays. Basically, if you get hence if you have started with a bad array, there will be the sparsing corresponding to a sequence of ideals, hereditary ideals, and it also will be bad. Okay, that's kind of the proof. And this is kind of, and basically it's kind of enough to do it for the star version, because actually this non-star version, it has less things being, it has less things being compared. Had something was a bad sequence there, it also will be a bad sequence for the star version. Okay. Okay. So the next claim is, okay, how much time do I still have? Okay. So the next claim is this combinatorial characterization of this Q less than omega orders, or ideals of Q less than omega. And this is basically very much inspired by a result of Kapil and Puzan about characterization of ideals for Higman order. So this, okay, so this theorem. Basically, so each ideal, to remind you, ideal of well partial order is downwards closed, upward directed set over P less than Q, P less than omega, where P is WQ, is a finite product of ideals of two following forms. Right, so first form is simply some R, where R is an ideal over P. And second form is R star, or R less than omega, where again R is an ideal over P. Right, so actually I think I haven't explained a few things. So basically when I talk about products of ideal, I mean pointwise product. As basically the product, we say that product of two sequences is simply a concatenation of the sequences. And product of the ideals is this kind of ideal consisting of pointwise products. Yeah, so R1 times R2 is R1 times and when I'm talking about this R less than omega, basically I consider all possible finite products of elements of R, or in this case, it's just kind of sequences built of arbitrary sequences built of elements of R. Okay, that's kind of characterization. And yeah, I also want to note that, of course, these two kinds of ideals are primes from this perspective of this product iteration, right? They are multiplicatively indecomposables. Okay. Yeah, so actually, no. I would say no. I think kind of, actually, we are giving new proof of this. Like, I think kind of they have, it's a bit hard to say. So basically, I think this paper was in French. We are like not 100% sure what precisely was the technique, but as far we can say it's what we're doing is different. The strength of the probably, let's say, should be proven ATR₀. So I mean, like this kind of technique is fit with that. So basically, I mean, you need to know that basically what you need to know is that if P is well-quasi-ordered, then P is non-Vegas well-quasi-ordered. And after that, like I don't think like there are much proof theoretical strengths afterward. Okay. Yeah, and basically, yeah, so basically we develop this. I think, yeah, so basically we develop a new method of proving the statement, which is kind of using basically this fairly abstract considerations about like how well-quasi-ordered monoids behave, and this is what allows us to kind of then generalize this to the characterization of transfinite iteration of ideal iteration. And so basically the key idea is that okay, so. So this here, of course, we have been dealing with this particular case of quasi-order on finite sequences, but in general, we can deal with well-quasi-ordered monoids. Well, quasi-ordered monoid is a monoid where we have on top we have an ordering. The ordering is well-quasi-ordered. And kind of multiplication operation is monotone in both arguments. And finally, identity happens to be the least element of well-quasi-ordered. Or equivalent, we can define well-founded monoids. Okay, and so else we need kind of, yeah, so else technically we need one additional property on top. Which, yeah, it's a bit technical, I think. Yeah, it's probably it's like, yeah. Anyway, I can state the property. So let's say ordered monoid is plus ordered monoid if, yeah, given for any PQR from M, if P less than or equal than Q times R, then there exists Q prime less than Q and R prime less than R, such that P is equal to Q prime times R prime. For some reasons, it happens to be an important property. Anyway, I guess I don't have enough time to go into this combinatorics why this is important, but it's kind of quite natural. Okay. Yeah, so actually, what else I should note about well-founded monoids is that, in fact, all well-founded monoids admit prime decompositions, right? So you kind of have this multiplicatively decomposable element that is primes, and then you could show that every element in well-founded monoid happened to be a product of finitely many primes, which is basically quite trivial result that relies on well-foundedness of the monoid. Okay, so, and basically this is what we need, right? Basically we kind of, what we really show is if we have a plus well-quasi-ordered monoid, and then we consider ideals of it, that then ideals form a plus well-founded monoid. Yeah. So if is plus monoid, then ideals are plus well-founded monoid. And basically we have analogous characterization of this ideal. So each ideal in this case is either an ideal either an ideal of primes, basically primes that corresponds to basically in the case of Higman ordering, primes have been simply sequences of the length 1. Right? So and here the characterization is each ideal is either an idea kind of an idea. So any prime ideal is either an ideal of primes of previous or kind of order, or it is a star of ideal of primes. Monoid and each and primes of this are of two types. First type of prime is that we have primes of original monoid. R that are elements of so that are themselves ideals over primes of original monoid, or secondly, they are R star. Where R is an ideal of the original monoid. Basically, it's fully analogous to the previous case, and since basically any ideal is a finite product of prime ideals. Okay.
That's a plus order?
Yes. Yes. Okay. Yeah. I don't know. Maybe it's not very.
This does not generalize some multiplication.
Sorry. No, it's not multiplication natural. It is kind of more like concatenation. Yeah. Sorry. So what?
This fails for multiplication.
Okay. Yeah.
Yeah, it doesn't hold.
Yes. Anyway, so this is so basically we have this characterization of this prime ideals, and then basically what we're really doing is that we're embedding. So if you look at this embedding that we need, right? So we're embedding. So what we claim is that we're embedding these ideals of this order into sequences of the set. So really, what we're doing is we're embedding prime ideals of this or kind of this q less than omega. So basically, I can consider, of course, we can have these primes of this I alpha dot star of q less than omega, and then we do these quasi embeddings of them into these orders. So this is basically what's happening. And the key here is, of course, like this characterization from this lemma allows us to go from kind of alpha time iterated ideals to alpha plus 1 times iterated ideals. Basically, of course, so what we know is that, that I alpha plus 1 star of q less than omega. So this, of course, is isomorphic to ideals over I omega. So it's kind of, we have this isomorphism, and basically, if you know how to characterize primes, primes of this well-quasi-order monoid, then we by this lemma we have a characterization of primes of this well-quasi-ordered monoid. And actually, it's very simple. Right? Basically, you take a kind of ideal of these primes, and then you either say it's just the ideal of the primes, or it is this basically this kind of basic closure on the multiplication of this ideal. Just exactly two options here. Yeah, and basically, yeah, and like this is just some very simple tricks how this allows us to embed these orders into this v dot alpha of q union alpha. So basically, the idea is that so we kind of for ideals on primes. So basically, for ideals on primes that are of kind of first form, we basically embed them to just this sets of all the pointwise images, and for the ones that are stars, we also add like this extra new ordinal that we have, and we embed them there to this kind of pointwise image from by the previous embedding plus this extra label essentially, and this does the trick. Okay, so so basically, so this is kind of how it works. So now hence we conclude with the following result. And okay, so result would be this. So, okay. Indeed. Theorem. So if in ATR₀, so if Q is a beta quasi-order, then every alpha Q less than alpha is beta quasi-order. Whereas, of course, the crucial case was the case of when alpha was equal omega. Okay, so this is basically the result. And so with regard to formalization in ATR₀, so basically this is basically the point is that this technique was fairly explicit in what it was doing. So we kind of just essentially have been dealing with like more. Okay, so the technique is these orders are very large, but the point is as long as you know that the things what you're dealing with is beta quasi-orders, so are beta quasi-orders, then in fact there is countable denotation system for them. So because in fact, because when you have a downwards closed set over well-quasi-order, then it always can be characterized by finitely many forbidden elements. And basically this allows you to kind of to have the denotation systems for this, countable denotation system for these orders and effectively work with them over say over ATR₀. Technically, of course, it's much more convenient to do it over ATR₀ set, or even better to do it over like set series where you have explicitly your elements in them. So in fact, in our paper, we use set series with this weak primitive recursive set theory with your elements. It's the most convenient system where you could work with these notions. But basically, the point is that, of course, so if you simply don't care about this theory, then you simply can do it over ATR₀ and just effectively code things in countable way. And since again everything here is fairly explicit, there are no real subtleties in the argument, and things work. Okay. So I think that's all I wanted to say.